Welcome everyone to this month's Quantum Gravity Across Approaches seminar in our seminar series on observations. So on possible observations of quantum gravity. And after a bit of a break, we return with our seminar, with a seminar about cosmology. So possible constraints from cosmology and possible observations in cosmology from different approaches of quantum gravity. And we are very happy to have our two speakers here, Edward Wilson-Ewing from the University of New Brunswick, who will present the perspective of loop quantum cosmology, and Kostas Skenderis from the University of Southampton, presenting a perspective of holographic cosmology. And before we start, just a brief reminder, our setup is that we have two talks, roughly half an hour, during which we would like to have short, more understanding questions. And afterwards, after both talks, we still have 30 minutes for discussions. But if you also want to ask questions, you can also use the Zoom chat. We also have the option to ask anonymous questions via a Google form. So Aaron has posted that in the chat right now. And also there's a Slack channel for Ed's and Kostas talks, where you can ask questions after the talks are over. So without further ado, Ed will open the round of two talks, and we're very happy to have you, and we're looking forward to both your talks.
All right, well, thank you very much for having me. So I'll start and I'll say a little bit about loop quantum cosmology. So as Sebastian said, I have half an hour to give a presentation on this. My goal here is really to give an introduction to this to non-experts, and also maybe to highlight a few results that I think are particularly interesting. Of course, in half an hour, I won't be able to cover everything, so I apologize to those people whose work I won't be able to present. If you're interested in more details, there's this review which I wrote a number of years ago, which has some of the information, and a more up-to-date review should be appearing sometime soon this summer. Okay, so let me start with a motivation. So this is very broad. So I think for anyone working in quantum gravity, they should be interested in cosmology, because I think it's an ideal testing ground for quantum gravity, no matter your preferred approach. So first, cosmological spacetimes are relatively simple. So of course, trying to do quantum gravity in general gets very complicated very quickly. But if we're just looking at a cosmological spacetime, often there are some important simplifications that arise and make it easier to have calculations that are tractable. So on the one hand, we have some simplifications that make calculations possible, but also this is something which is very relevant from an observational point of view. So we do expect quantum gravity effects to be important in the very early universe. So first, in classical general relativity, we have a Big Bang singularity. And presumably, quantum gravity effects will become important when the curvature becomes very large, and could possibly resolve the Big Bang singularity and replace it by something else. So the question is, what is this something else that quantum gravity brings in? And also, if we have quantum gravity effects in the very early universe, the natural question to ask is, do these effects leave any signatures? So are there any observational consequences that we could see, for example, in the cosmic microwave background? So I think these points give a very strong motivation to look at cosmology from the perspective of quantum gravity, no matter your preferred approach. In my talk, I'm going to focus on loop quantum cosmology. So this is one particular approach, which is based on loop quantum gravity. Okay, so the main steps in loop quantum cosmology are the following. So the first thing that we do is that we impose the symmetries of the cosmological spacetime that we're interested in. So typically, this will be a Friedmann spacetime. So we impose homogeneity and isotropy. Once we've done this, there are only a finite number of degrees of freedom that are left. So of course, in quantum gravity, this is a field theory. But when we're looking at loop quantum cosmology, we impose the symmetries that we want ahead of time. So now we only have a finite number of degrees of freedom. So this is really a mechanical system. Okay, once we've imposed the symmetries, then we write the dynamics in a Hamiltonian form using the same type of variables as what we would do in loop quantum gravity. So I'll say a little bit more about this in the following slides. Then, once we have the dynamics in the Hamiltonian form, we can then build the quantum theory. And this quantum theory is based on operators that encode areas and holonomies. So these operators are analogous to the operators that we have in loop quantum gravity. And finally, another important input from loop quantum gravity is that there's an area operator in the full theory, and this area operator has a discrete spectrum. And in particular, it has a smallest non-zero eigenvalue. This is typically denoted by a capital delta, and it's of the order of the Planck length squared. So these are the main steps that we follow in loop quantum cosmology. So just to recap, first we impose the symmetries of the cosmological spacetime. And then afterwards, we quantize this system using the same steps as we would in loop quantum gravity, except now we're dealing with a finite number of degrees of freedom rather than a field theory. So this makes it a lot easier from a technical perspective. Okay. So let me give you a little more in the way of details. So I'll start by looking at flat Friedmann-Lamite Robertson-Walker or FLRW spacetimes. So we have a very simple metric with a single degree of freedom, which is the scale factor. So this really is just a very simple system with 1 degree of freedom. Of course, there can be matter content too. I'll discuss matter later. For now, I'll just focus on the geometrical side in terms of the gravitational degrees of freedom. So in this case, just 1, the scale factor. Now, I want to rewrite this in terms of the variables that we use in loop quantum gravity. So this is in terms of the Ashtar-Barbero connection and the densitized triad. I don't want to go into too much detail here, but the point is these are phase space variables. They're canonically conjugate. And because we have a single degree of freedom, that means we have a 2-dimensional phase space. And so we have our variables C and P here. And because the metric is very simple, it's diagonal, that means that my connection is diagonal also, and my densitized triad is diagonal also. So the index structure is pretty trivial in this case. I'll be using these phase space variables C and P going forward, but to connect back to the scale factor, you can think of C as being something like the velocity of A and P being the scale factor squared. Okay, and these, as I said, are canonically conjugate variables. Now, I want to have a Hamiltonian form so I can pass more easily to the quantum theory. So the ADM Hamiltonian for a flat FLRW spacetime, again, using these variables, has this form. So I have my densitized triad, which shows up twice here, so I'll get a P squared. And then I have my field strength, or if you prefer, this tells us about the spacetime curvature. And this is essentially C squared. And from this Hamiltonian, just classically, I can extract my equations of motion from my theory once I make some choice for the matter content. And the equations of motion are exactly the usual Friedmann equations that you would get just from standard Einstein gravity. So this really is just rewriting the classical theory in different variables, but in an entirely equivalent way. So the only thing that I've done here is I've rewritten the theory in a way that will make passage to the quantum theory a little bit easier. But otherwise, this is entirely equivalent to what you would get if you just looked at the classical Einstein equations. Okay. Now, one of the basic objects I'll want for the quantum theory is the holonomy. And so when we calculate the holonomy of a connection, we're calculating that along some edge. And this will give us information about the curvature felt along that edge. Now, here we're really interested in these simple cosmological spacetimes. So it's enough to just look at holonomies along edges that are straight. So here I'm going to construct these holonomies that are along a straight edge, so something like this, and it has some coordinate length lambda. So this is the general form. So I'm integrating over some coordinate length lambda, and I have my connection here. So this is an SU2 connection. So these are my generators of the SU2 Lie algebra. Okay, I don't want to spend too much time on the details here. The main point that I want you to take away from this slide is that the holonomies are the basic objects that we'll use to capture the space-time curvature. And for this space-time, because it's so simple, the dependence of the holonomies on C is entirely captured by linear combinations of complex exponentials. So if I look at complex exponentials of C like this, I can do a linear combination to get this cosine and this sine term. So what that means is that instead of working with these group valued objects, I can work with something simpler and just work with this, because my holonomies have such a simple form that I can construct any holonomy I'm interested in out of linear combinations of these complex exponentials. So this is what will show up in my quantum theory. Again, because these cosmological spacetimes are so simple, this is why this can be done in this case. Okay. Now, I've already told you that from the holonomies we can get the curvature, so I want to say a little bit more about how that works. So if I take the holonomy around some loop, so this little box here is meant to be a loop, so you can think of it as this loop here on some surface. So if I take the holonomy of my connection and I subtract the identity and I divide by the area of this loop, and then I take the limit as the area of that loop goes to 0, I recover the field strength or the space-time curvature. So the calculation in this case is very simple, and I just have this quantity here. And you can see that if I take the limit of lambda going to 0, I just get c squared back, which is essentially the field strength. And I want to point out here that this is very, very similar to what is done in the lattice gauge theory. So if you have a gauge theory that you're putting on a lattice, the way that you will often calculate the field strength is by taking the holonomy around a closed loop and then calculate the field strength in the same way. So this is very similar in that respect. Now, the main difference comes from an input from loop quantum gravity. So as I mentioned at the beginning, in loop quantum gravity, we have an area operator, and this area operator has a discrete spectrum. So what that means is that classically, I want to take this limit of the area going to 0. But in the quantum theory, this limit just doesn't exist, because the area, as I said, has a discrete spectrum. And so you can't take the limit of the area going to 0. So 0 is an eigenvalue of the area operator, but you can't get arbitrarily close to it. There is a smallest non-zero area, so this delta, but you can't get any closer to 0 than that while remaining non-zero. So this limit here that I would want to take in the classical theory, I just can't take in the quantum theory. It doesn't exist. So instead, what we do is that we ask that the area here be the smallest possible without being 0. And we ask, and so the smallest possible area is delta. That's again, the smallest eigenvalue of the area operator in loop quantum gravity. And we want to set the area equal to delta. There's one point that we have to be a little bit careful about here. And this is that this lambda here is a coordinate length. Right, so this is a length with respect to the coordinate x. The physical length in a cosmological spacetime is the coordinate length x times the scale factor. Right, so it's important to keep the scale factor in mind here. So if we want this to be a square with equal lengths, then we want each length of this square, so the physical length will be the scale factor times lambda. We want that to be equal to the square root of delta. Or I can isolate lambda, and it gives this expression in terms of delta, so the smallest area smallest non-zero area eigenvalue of loop quantum gravity divided by p. Remember, p is just the scale factor squared. So this is the one key input from loop quantum gravity. We have this minimal area, which means that the classical limit that we would take here doesn't exist. Instead, we have to fix this area enclosed by the holonomy to be the minimal one possible. Okay, so that's how we can construct an operator corresponding to the curvature in a theory. And now I'll give a quick sketch of how we get the quantum theory. So the basic operators on the Hilbert space are these complex exponentials, which encode the holonomies, and p, which tell us about the area, right? So p is a squared, so of course that tells us about the physical area of some region. So I can express my Hamiltonian in terms of these operators, and in particular, I substitute this expression for the field strength, as I explained earlier, by taking the holonomy around this loop of minimal area. Now, I won't show you the details because it's not particularly illuminating, but as a result of this, we get an operator, and it turns out that this is a difference operator. Often when you get a Hamiltonian, you'll get differential operators. Here we get a difference operator, and this shows up because we have this discreteness due to the introduction of this minimal area. So what this means is that we have dynamics that relate states with different values of the scale factor, which are separated by a discrete amount rather than some continuous relation. Okay, and once we have our Hamiltonian operator, we can look at the quantum dynamics and see what happens. Typically, this has to be done numerically, but in some cases, for some careful choices of factor ordering, it turns out we can actually solve it analytically also. So let me tell you a little bit about the results. Of course, if you want to look at the dynamics of a state, we have to choose some initial state. And here, today, I want to avoid making any assumptions about the Planck scale. So what I'll do is I'll set initial conditions today. So today, we know that our universe looks very classical. So we can take our initial conditions to look like today. So this is a sharply peaked state around a classical solution. And then with using this initial condition, we can evolve backwards in time towards the high curvature regime when quantum gravity effects will eventually become important. And this graph shows what happens. We have a wave packet here that you can see, and then we evolve it back in time. So this here is the volume, and this is time. Here I'm assuming a radiation dominated universe, but other choices are possible. And we see that it goes back in time, it reaches some minimum volume and then bounces out. And this is a very generic result that the Big Bang and Big Crunch singularity are resolved, and they're replaced by a non-singular bounce. And what we find is that classical general relativity works very well for a sharply peaked state like this, so long as you're far away from the Planck regime. So long as your space-time curvature is small compared to the Planck scale, then the quantum effects are negligible, and the expectation values of your wave packet follow what you'd expect from general relativity very closely. But then when you get close to the Planck regime, when the curvature becomes Planckian, then you have these effects that show up that cause this bounce to happen, and then the singularity is avoided because of this. Okay, so this is something which is very generic. Here I gave an example for a state that's sharply peaked, but you can also look at states which have large quantum fluctuations. Then the quantum dynamics is a little bit more complicated, but the singularities are still resolved and you still have a bounce. One thing that I want to point out here is that because I started with a state that was initially sharply peaked, it actually turns out to always remain sharply peaked. And this is something that was a little bit surprising at first. But it turns out that the degrees of freedom for a cosmological spacetime, essentially the scale factor, these turn out to be degrees of freedom that are very heavy. So if you assume that the quantum fluctuations are initially small, let's say today, and then you evolve them through time, you'll find that they always remain small. Okay. So if you have a sharply peaked state, then it's often enough just to track the evolution of expectation values. And in loop quantum cosmology, this can be done using what are known as effective equations. So these capture your leading order quantum gravity effects, including the bounce, but they ignore quantum fluctuations. And what we get for the Friedmann equation has this form. So classically, it would just be this here. And then we have this extra correction term here. And we see that the bounce, when the Hubble rate is equal to 0, happens when rho is equal to the critical energy density rho c, which is at the Planck scale. And so this is an equation that we can use for sharply peaked states and will tell us how our expectation values evolve. Okay, so with that, I've said what I wanted to say about the background, the homogeneous space-time geometry. And so I answered the first question that classically we have a Big Bang singularity. And once we include quantum gravity effects in the quantum cosmology, what we get is a bounce, and there is no singularity anymore. Now, in the time I have left, I want to say a little bit about observations. I realize I'm running a little bit short on time, so I'll try to be a little bit faster here. But let me just say that to make contact with observations, and in particular with the cosmic microwave background, which we know a lot about, we have to include perturbations. So what I've said so far is really just talking about a Friedmann universe. But if we want to match the cosmic microwave background, we have to be able to understand the dynamics of these perturbations. And one thing I want to emphasize here is that loop quantum cosmology really tells us how to quantize gravity, in a sense. It doesn't tell us anything about the matter content. So just like general relativity, if you include different types of matter, you'll get different types of predictions. So if in loop quantum cosmology we include an inflaton field, then we'll get inflation with certain types of predictions. Whereas if we include a different type of matter field, for example, an ectorotic field, then we'll get something different. So in loop quantum cosmology, it's really important to understand that the predictions come along with the matter field. So you have to make a choice on the matter field you're interested in, and depending on that, you will see certain types of effects. Very quickly, I want to mention that there are several approaches to cosmological perturbation theory that have been developed in the field. I'm running short on time, so I won't say much about this. I just want to say that each of these frameworks rely on different approximations and truncations. So depending on the calculation that you're doing, different approaches may be better suited for the calculation. But let me say a little bit about some physical intuition behind the types of effects that we expect to see. And then I'll say a little bit about what we could see in the CMB. So we're looking at linear perturbation theory. So we can look at just the Fourier modes. And at small scale, so if we have a Fourier mode that has a short wavelength, these perturbations don't feel a space-time curvature. So they evolve exactly like they would in Minkowski space. So to know about the curvature, you have to look at Fourier modes that have a wavelength which feels the space-time curvature, which is essentially the Hubble radius. So 1 divided by the Hubble rate. So that gives you a scale in the universe, and your modes that are greater than that will feel the space-time curvature and react to it. So quantum gravity effects are important in the very early universe. And the modes that will feel quantum gravity are those that have a wavelength greater than the curvature radius at the bounce. The curvature radius at the bounce, of course, is the Planck length, because we reached the Planck curvature. So the modes that we're interested in the CMB that have a chance of knowing about quantum gravity effects are those that have a wavelength which is greater than the Planck length at the bounce. And so the question that we have to ask is whether these modes can be seen today or not. And that really depends on the cosmological model. So let me start with inflation. So if we have inflation and we look at the modes that we see in the CMB today, we track them back. We look at the evolution backwards in time. It turns out that if there are about 60 E-folds of inflation, then the LQC bounce can leave an imprint on the CMB at large scales. So we have some cosmological modes here that we can see today in the CMB. Here we're looking at inflation when those modes exit the Hubble radius. And if there are 60 E-folds, we track them back, and at the bounce, some of them are greater than the curvature scale here. So these modes, which are greater than the curvature scale, will feel the quantum gravity effects at the bounce, and they could be modified and show up in the CMB with some signature. Now, one thing that's very important to keep in mind is that this really depends on the number of E-folds of inflation. If you have more inflation than 60 E-folds, let's say you have 80 E-folds of inflation or 100 E-folds of inflation, then these modes that feel the curvature at the bounce are super horizon today, and we can't see them. So we only expect some observational effects if there are sufficiently few E-folds of inflation. Now, if that does happen, then LQC has some effects, and it could potentially generate the power asymmetry anomaly that's seen, or give low power at large scales, and also amplify certain types of non-Gauss sanities at large scales. Because I'm short on time, I won't go into this in too much detail, and I'll just refer you to these papers. But the key point here is that for inflation, there can be effects at large scales in the CMB. There are other early universe scenarios that don't depend on inflation. Those are also possible in loop quantum cosmology. So one possible alternative is the matter bounce. And in this scenario, we have scale invariant perturbations that are generated in a contracting universe. So you don't need inflation after the bounce. This is a different way to get the scale invariance that we see in the CMB. Now, for the matter bounce, it turns out that all of the modes that we see in the CMB were super horizon during the bounce. So they all felt quantum gravity during the bounce, but they all feel quantum gravity in the same way. So it turns out that the main effect from loop quantum cosmology in this case is that you can suppress the tensor to scalar ratio. And this is a quantity that has quite strong bound observationally. So it's interesting that LQC in this context can suppress it. One thing that you have to worry about in these in the matter bounce scenario, though, is anisotropies, because these can grow very significantly. And it turns out that there are some very strong observational constraints on these anisotropies once you look at the CMB. So this is work that should be appearing soon. Okay, so the main takeaway message here is that if we want to make contact with the CMB, we have to look at perturbations. There are ways to do that, but the predictions really depend on the scenario that we consider. I think I'm almost out of time, so let me just end by mentioning two open questions, which I think are very important for loop quantum cosmology. So as I've explained, loop quantum cosmology is motivated by loop quantum gravity, but it isn't derived from it. So we follow the same type of steps, but it would be nice to be able to start from full loop quantum gravity from a field theory, and then from the quantum theory, then impose the symmetries and find a state that corresponds to cosmology, for example. And so the question is, can we fill this gap between loop quantum cosmology, which is motivated by loop quantum gravity, and actually try and derive it? So there's been some work on this, but there's still a lot that remains to be done on this. So I think the early work is quite promising, but still more has to be done. And another question has to do with the perturbations. So a key input for loop quantum cosmology, as I've explained, is that we have this discrete spectrum of the area operator in loop quantum gravity. And this shows up when we want to define the curvature operator that shows up in the Hamiltonian. But if we have this discrete spectrum in the geometries, we have a geometry that has a discrete nature, does this imply somehow an ultraviolet cutoff for perturbations? So this is an open question. I don't think we have a clear answer to this yet. But if there is an ultraviolet cutoff, then how could this be handled consistently? So this is something that's been thought about very generally by a number of people. And I think it's still unclear how this could be handled if it's necessary. So these are two open questions that I think remain to be addressed. And hopefully we'll have some answers to this in the near future. So I think I'm out of time, so let me just summarize. So loop quantum cosmology is based on loop quantum gravity. It's the key inputs are that we use the same types of operators, and we use the input that we have a discrete area spectrum. We find that the Big Bang singularity is replaced by a quantum bounce at the Planck scale. And we can also look at cosmological perturbations and get some predictions for the CMB. So in inflation, we can potentially have some effects at large scales. And in other approaches, we can have different types of effects. For example, in the matter bounce, we can have a suppression of the tensor to scalar ratio. And I just mentioned these open questions. So with that, I'll stop here and thank you for your attention. I'll be happy to take any questions you have.
Yeah, thank you very much, Ed, for this very pedagogical talk. We're still in the time for quick questions after the talk. So, Georgia, do you have a quick question for Ed?
Just a quick conceptual question. Thanks for a very nice review, but what happens to unitary evolution? This is a conceptual question. No, it's maybe related to the last two things. What happens to unitary evolution in this approach to quantum cosmology?
Right. So everything that I've said is unitary. The question you're asking about, I think, is this.
Yes.
Right. So far, the approaches that we have for cosmological perturbations, there is no cutoff. So in this case, we just have all of the modes, and that they're always there. Now, the question is there an extra ingredient that we should add that would bring in an ultraviolet cutoff? And if the answer to that is yes, you're right, that then unitarity will be a tricky question. So at this stage, everything is unitary, but if the answer to this question is yes, then the second question is very important, and in particular, consistently, for me, means can it be made unitary in some way?
So it's an open question.
Right. So I would say that what we've done so far, everything is unitary, but there's this effect that if it does show up, and this isn't sure, but if it does show up, then it's an open question of how to handle it.
Okay, thank you.
Yeah, you're welcome.
Okay, another quick question from the chat. Does the entropy of the universe increase across the bounds in LQC?
Right. So this is a question that you can ask on several levels. If you're just looking at the background, so just a Friedman universe, then the entropy won't increase. If you're looking at perturbations, then perturbations typically will grow in a contracting universe. And so you can say that in some way, the entropy will increase in the contracting universe and up to the bounds. I think to make this precise, it's important to say exactly what you mean by entropy. And I think there are a few different proposals for what that could be in cosmological perturbation theory. In general, I think that for all these different choices, you will get an increase once you include perturbations.
Okay. Yeah, I don't see any further questions at the moment. So thank you, Ed, for now.
Okay, thank you.
And we move over to Kostas.
Okay, let me share. Okay, can you see my screen?
Yes, we can see it. So Kostas Skenderis will now continue with holographic cosmology and cosmological observations.
Okay, thank you very much for the invitation to talk to this very interesting seminar series. So I will start with just a brief review of some of basic questions that connect cosmological observations and quantum gravity, and then we're going to move on to introduce this framework of holographic cosmology and see how it fits within this general questions. So these core questions are basic questions, but I would like to put them forward just to put the context, kind of a bit of the bigger picture. I think perhaps the most basic cosmological observation, which we do not currently have a theory to explain, is why do we have an arrow of time? I think a common viewpoint is that this has a thermodynamic origin, but that just rephrases the question. So if the entropy increases, this means we have to have started for something which was very low entropic. So just rephrases the question from why we have an arrow of time to why we had initial state of a very low entropic initial state. So one of the things I would like to introduce a framework which at least conceptually explains this part. Now, when we go to quantum gravity, Ed already explained the issues with general relativity and the initial singularity. So I would like to understand what happened at the initial singularity. Was there something before this initial singularity? Can we formulate the laws of physics if there's no space and time the way we perceive it today? And if we can, are there any observational signals from this period? And now going back to observations, we know that we see our universe and we observe a CMB and we know it's uniform and isotropic. Why is this the case? And so we observe a distribution of galaxies. Can we explain why the galaxies are distributed the way they are? So this is some of the kind of bigger questions I would like to have the theory answering. Okay, so what I would like to argue is that holographic cosmology does provide the right framework to answer these questions. So holographic cosmology, first and foremost, is a new framework for cosmology. So in traditional cosmology, we have some theory in space-time in 4 dimensions and some matter, and we try to quantize that model in some way, either perturbatively around some FRW, or we just start to talk how you could try to do this using loop quantum cosmology. In holographic cosmology, you replace that piece of data with a new formulation. So you formulate a theory in terms of some 3-dimensional quantum field theory that has no gravity, and you provide a dictionary that relates observables of this quantum field theory to 4-dimensional observables. So this new framework includes conventional inflation, and I will very briefly mention this later on, but also allows for new models which describe a non-geometric, very early universe, kind of a paradigm of what it means to have a description when space and time, the notions of space and time do not make sense. Okay, so why would one care about this? First of all, these models are fully consistent with quantum mechanics. They're based on quantum field theory. General relativity emerges when the dynamics and quantum field theory become strongly interacting. These models are well defined when traditional general relativity breaks down at the initial singularity, and we'll see an example later on in this talk. And also has explains the hour of time, has a very intuitive explanation of the hour of time. And finally, it really fits the data. So this is from a paper I did with Nayash, which I think it is in the audience, where we compare the predictions of holographic cosmology of the models that I will describe in a minute with CMB. So this diagram has both lambda CDM, that's the blue curve, and holographic cosmology, that's the red curve. And as you can see, you cannot distinguish them by the eye, and I will become a little bit more quantitative later on. And this insert is the low L region, which will become important later on as well. So if one looks at the residuals, which are shown here, so here we have this green region is the error bar from Planck, and this black curve is the difference between lambda CDM and holographic cosmology, and the blue dots are Planck minus lambda CDM, and the red asterisk are Planck minus holographic cosmology, and also you can see pretty much the difference between the models is within the error bar. So the actual data cannot distinguish between kind of conventional lambda CDM and this new models that describe a non-geometric very early universe. Okay, so I'm not going to be able to give you all the references. So this work starts almost 20 years ago. So the early works from that come under the name of the Sitter CFT, or the wave function of the universe. What I will describe, the general setup was built about 10, 12 years ago in the papers with McFadden. And the very last part, where I will describe the resolution of the initial singularity, is based on ongoing work I'm doing with lattice groups. And we published one paper last year, and there's more work to come. And if you want more references, just ask me afterwards. Okay, so this is a general talk, so I'll try to give the general ideas rather than the technical details. So to do this, I first need to give you at least the punchlines about what are this gauge gravity dualities, the basic features. So the three main features which are important. First of all, this is a weak strong duality, which means that one of the descriptions is strongly coupled, the other is weakly coupled. So this means that if we're interested in describing a strongly coupled gravity, like at the place where you have an initial singularity, you should be looking at a weakly coupled quantum field theory, and vice versa. If you're looking at a theory where gravity is weakly coupled, then the quantum field theory would be strongly coupled. Then there is a so-called UV-IR connection. So this means that the ultraviolet of the quantum field theory is the infrared of the gravity, and vice versa. So this means that UV issues of quantum gravity are related with the IR issues of quantum field theory. And finally, so in this holographic dualities, we relate a four-dimensional universe with a three-dimensional theory. So one can ask, what is the additional direction? So this holographic direction is associated with the energy scale with which we probe the quantum field theory. So if you have a quantum field theory, then the observables depend on at which scale we probe the theory. And this is captured by a so-called renormalization group flow. So as you go from kind of high energies to low energies, you have a coarse graining of degrees of freedom. So what might be three distinguishable things here, then at very low energies, they're coarse grained to look like one. And as we go from the UV to the AR, quantum field theories comes with a monotonic coarse graining description. And this is going to become important in a minute. So the normalization group scale corresponds to this additional direction. So we have the three-dimensional theory, and you can think of it as at different energy scales, you have a slightly different description, and that gives the additional direction. Now, when we go to cosmology, then it's really the normalization group flow which corresponds to cosmological evolution. More precisely, cosmological evolution is inverse normalization group flow. So here on the right, we have the conventional description of our universe, where we start with some initial singularity where gravity is strongly coupled. And as time moves on, we go to a weakly coupled gravity. So on the right, we have the same description, but now on the quantum field theory, where now the initial singularity is the infrared of the quantum field theory, and the future is the UV of the theory. So that already gives a slightly different perspective on the dynamics in gravity. So in gravity, usually we say we give some cosine data here, and we want to know how the system evolves over there. But here, what this holography tells us is that actually you should more view things in terms of effective field theory. So if I give the theory over here, then I can describe everything to the past. But then with only data here, I have only limited information about going forward, because I try to go opposite to the normalization group flow. On the other hand, if I give you the quantum field theory at the far future, at the end of time, then I know how to describe entirely the entire history of the universe in the past. Now, this association of cosmological evolution with normalization group flow already explains the hour of time, because now the monotonicity of the normalization group flow explains why we see an hour of time. And we also know in quantum field theory that as we go to the UV, there are more UV degrees of freedom. And the dynamics in the IR are universal. So the universality of the infrared dynamics explains the initial conditions. So the initial conditions are natural just by the universality of infrared dynamics. Okay. Now, if we want to associate normalization group flow with cosmological evolution, we can ask, do the universe that we actually see today has any features of normalization group flow? And the answer is yes. So perhaps the most basic feature of normalization group flows is that it interpolates between fixed points. And currently we know that we live in an area which is dominated by dark energy. And the universe, so if this is a cosmological constant, then the universe would go to the city universe in the future. That corresponds to a conformal field theory on the other side. So indeed, our future goes towards a UV fixed point. So that would be a strongly coupled UV fixed point, which would correspond to a positive cosmological constant in this context. Or we could also live in a phase which is coupled, which is described by strongly coupled supernormalizable theory, and that would correspond to the dark energy driven by quiescence. Now, in the very early universe, we expect that there was a period of inflation, so that would correspond to an infrared fixed point. So we see that indeed the cosmological evolution looks like it is driven by an evolution between two fixed points. But what I will argue today is I will argue for a slightly different viewpoint where the infrared is governed by a supernormalizable theory, which would, in conventional language, would correspond to the power law inflation. Okay, so this is the conceptual underpinnings. So this is my one slide with the formulas, because we're going to connect between computations in quantum field theory to cosmological observations. And the basic cosmological observations that we have in our disposal are the power spectra and non-Gaussianities. And for those, there are very concrete formulas. And here I'm just giving you the formula for the scalar power spectrum and the tensor power spectrum. So this is related to the two-point function of the energy momentum tensor in the dual quantum field theory. So here I give the two-point function in momentum space. And in all dimensions, this two-point function is governed by two scalar quantities, this A and B quantity, and this is distinguished by the index structure that multiplies them. So this part here is the transverse traceless piece of the correlator, and this is the trace piece of the correlator. So if you're given a theory like the one I will give you in a few slides, then you can just compute this, let's say either perturbatively, or if you can not perturbatively, then extract these quantities, then put them in these formulas, and this gives you the prediction of holographic cosmology for the cosmological observables. And there's similar formulas for non-Gaussianities. So if you want to compute the bispectra, then you need to compute three-point functions of the energy momentum tensor. If you want to compute the trispectrum, then you need four-point functions, and so on. And there are concrete formulas for all of those. Okay, so these are the formulas. Now let me give you the picture in a graph. So this is our universe. So we are here. So that would be the place where we have conventionally the kind of the hot Big Bang. And this period here is what people conventionally put inflation. But now I'll call this a non-geometric phase because it's not necessarily a phase of exponential expansion. So in the description that I will give, I'm going to put the dual quantum field theory to live roughly at the end of that period, which you can associate with reheating. And then the evolution afterwards is conventional evolution with Einstein's equations and radiation domination, matter domination, and dark energy. So if you're here and you observe the power spectrum, then you can see the correlations from 2 points in the sky going all the way back to the recombination period. Now, in this language, what you're doing is basically what you're observing is the correlation function between two energy momentum tensors, which are inserted in that surface. So this was this 2-point function here. One is inserted at this point and the other over there. So even though in this region here, there's no geometrical description, there's still well-defined laws of physics. Actually, this period here, this is the geometric description ends here, but the universe exists, say, at all times, because as we'll see in a minute, this description here is finite in the infrared. So the theory can go to arbitrarily low modes over here, and that would describe the universe at earlier and earlier time. So there's no beginning of the universe. The universe exists forever. So there is some timeless theory here that describes the universe in a period where it's non-geometric. Okay. Okay, so this is a general framework. So now let's move to discuss some concrete models. So there are no first principles way to find what is the dual quantum field theory, but we can use a bottom-up sort of approach. And if we want to describe a non-geometric universe, as I described earlier, we need to use a quantum field theory which is perturbative. So a general perturbative quantum field theory that involves only massless fields is given by an expression of this type. So this is a three-dimensional theory. We have some Yang-Mills theory. This is the Yang-Mills coupling constant, which has mass dimension 1. And we have some scalars with a 5 to the 4 interaction. In principle, we can include fermions, and we have included fermions in the papers. But the CMB data that I showed you earlier, they actually rule out theories which are mostly fermionic. So I'm suppressing them here. So this is the theory. So now once you have the theory, then you need to compute its energy momentum tensor and then plug it into the formula and see what results that you're getting. So here I will consider a theory which admits a Toft large N limit. So I will take all fields to be in the adjoint of SUN and consider a large N limit. Now for this type of theories, the form of the 2-point function is universal. And it is given by a formula of this type. So it has a factor of n squared because this is a large N theory. So that's how large N theories behave in the large N limit. Has a factor of q cubed because the energy momentum, the dimension of the energy momentum tensor is 3 in 3 dimensions. And it's multiplied by a function of the dimensionless, by the effective dimensionless coupling constant. So even without doing any computation, this is the form. And then this means that the power spectrum, by plugging in this into the formula I showed you earlier, this formula here, then we find this expression. So now we see from here that the fact that the perturbations, the primordial perturbations are very small, means that n is very large. So the large N approximation is justified. And the fact that the spectrum is nearly scale invariant means that this function has to be nearly constant. Okay, so what happens in perturbation theory? In perturbation theory, this function starts with indeed a constant, and then there are perturbative corrections. So this F naught, F1, F2, and alpha naught are constants that depend on the specific theory, the field content. But very importantly, this expression also has an infrared divergence in perturbation theory at 2 loops, which is given by this term. So I'm going to come back to that term towards the end of the talk. So indeed, if you do perturbation theory, you do find that this F is nearly constant when the G effective is very small. Now for comparison, if you want to see how conventional inflation arises, conventional inflation arises when the theory we're considering is nearly conformal. So here I have a theory I had a dimensional parameter, but I could consider other theories which are conformal. and deform them with a nearly marginal operator. In this case, the analog of f takes this form over here. And we see that, and then from here, we get the conventional inflationary behavior with a spectral index. But in this talk, I'm going to focus on this type of theories. Now, for this type of theories, universally, you get the following predictions. So the scalar power spectrum takes the form which is given here instead of kind of the inflationary kind of behavior, which is like this one. So to get this type of behavior, you need to use a CFT. If you use this perturbative quantum field theories, you get kind of logarithmic behavior. So the same is true for the power spectrum. And then the non-Gaussianities are also universal. For example, and they have a very, very particular form. For example, there is no local non-Gaussianity. So if tomorrow an observation of local non-Gaussianity comes of any size, that will rule out all of these classes of theories. Now one can ask, do the data prefer this type of power spectrum or this type of power spectrum? And this is the question we asked with Nayesh about 5 years ago, and this is the plot I showed you earlier in this talk. Now to make it a little bit more quantitative, so when you fit to data, one finds that this G effective is indeed very small for all the scales seen in CMB, except at very low multiples. So a posteriori, we see that the assumption that we did perturbation theory is justified, except at very low L's. And low L's here means L less than 30. That's the place where you have the large scale anomalies that Ed also mentioned towards the end of his talk. Now, if you compare the two models using, for instance, goodness to fit, you find that chi-square cannot really distinguish between the two models. They really quantitatively do the same. And there is a model that satisfies all observational constraints. That's SUN gauge theory coupled to a number of non-minimal scalars with phi to the 4 interaction. Now, in the remaining of this talk, I'm going to further simplify this model by suppressing the gauge fields, by removing the gauge fields. So I will look as a model for the very early universe, a purely scalar model, a model of this type. So a single scalar, which is an SUN matrix and has a phi to the 4 interaction. So for this model, this is the energy momentum tensor. Non-minimal means there is a term that there is an improvement term with a new parameter. So this model has two parameters, the size of the matrix and this parameter psi. So the size of the matrix, of the SUN, controls the smallness of the primordial perturbations, as I described earlier, and psi is related to the tensor to scalar ratio. So with just two parameters, it looks like one could completely fit all the data. Now this model doesn't have gauge fields, so it's not perturbative all the way down to L equals 30. One needs to do again a custom fit to data, which we did. So the model becomes non-perturbatively around L equals 260. But in the region where it is perturbative, it actually about 2 sigma better than lambda CDM. So this model does better than lambda CDM in a regime where it is reliable. But of course, we cannot ignore this data. So to do this data, we need to a non-perturbative evaluation, which I will come in a minute. So let me briefly now address the singularity resolution. So I emphasize here there is a piece over there which is infrared singular. Now this infrared singularity, so the infrared of the quantum field theory is related to the UV of the quantum gravity. So the initial singularity, the fact that there is naively have an initial singularity is mapped in this case to the fact that the dual quantum field has a naive infrared singularity. So if this infrared singularity persists non-perturbatively, then the theory is just not predictive. But it was argued about 40 years ago in these two papers that specifically this type of theories I have been discussing, they are non-perturbatively infrared finite, where the coupling constant acts as an effectively as an infrared regulator. So since in holographic cosmology, the time evolution is inverse normalization group flow, so then this mechanism is a mechanism for the resolution of the initial singularity. So, so then to test this, whether this resolution is actually in action, and also to analyze the low L region, one needs a way to compute non-perturbatively the observables in the quantum field theory. And that's what I have been doing over the last few years with the two lattice group, the lattice group in Southampton and in Edinburgh. So this is a talk on its own, so I'm not going to give you the details, and it's still in progress even after a few years. So this is in a sense the checklist of what one needs to do. One needs to discretize the continuum model. It needs to find the massless point, which I will briefly discuss in the next slide. Then it needs to find what is the correct operator that corresponds to the energy momentum tensor, and then compute the two-point function, and finally compare with blank data. So let me briefly discuss this, because this is linked with singularity, with the issue of singularity resolution. So if I want to simulate a massless theory on the lattice, this means that you need to introduce a bare mass and fine-tune its value so that the theory, when you go to the continuum limit, becomes massless. Now, this bare mass, you can compute it perturbatively with diagrams, order by order. And one finds that this mass is affected by UV divergences up to 2 loops. That's not a problem because we know how to renormalize these theories. These are asymptotically free theories. But most importantly, these are infrared divergence from 2 loops. So perturbatively, we see explicitly the issue that Jekiv, Alperquist, and Franz found in the beginning of 80s, namely that there are infrared divergences, and if these are not resolved non-perturbatively, the theory is simply doesn't exist. So the paper I mentioned earlier on is was devoted to study this on the lattice. So we have shown non-perturbatively that this infrared divergences are indeed absent, and so this model indeed resolves the initial singularity in the specific context. So now that we have resolved the singularity, then one can ask, what are the predictions? And for that, one needs to compute the two-point functions, which were not there yet. So this is preliminary results, not for the correlator we want to compute, but for one which is a little bit simpler to compute. Instead of having the trace of the, instead of having the energy momentum tensor, one uses the trace of phi squared. So here I have various curves. So this is the 1-loop approximation to the correlator. This is the 2-loop approximation. And the axis here is the coupling constant. So perturbation theory is valid here. And all of the symbols here are described there, are lattice data. So you can see that the lattice simulation agrees very, very well with what we see perturbatively, and actually allow us to also compute the correlator non-perturbatively in the regime where perturbation theory is not valid. So now what we need to do is we need to do what we're currently doing is doing the same computation for the two-point function of the energy momentum tensor. Then once we extract the behavior here, then we can ask, how does this compare with data? So I'll have a few more comments in my last slide. So I think my time is almost up. So let me summarize. So what I try to argue in this talk is that holography offers a unified framework for discussing the very early universe. It includes conventional inflation in the form of strongly coupled quantum field theory, but perhaps more importantly, allows for qualitatively new models that cannot be described by any other means. So, and these new non-geometric models are based on weakly coupled quantum field theories or quantum field theories with a coupling of order 1. Since in these non-geometric models, Well, in all of these models, we get the out of time pretty much for free. That comes from the monotonicity of randomization group flow. And these models also allows for a new way to resolve the standard hot Big Bang puzzles, like the horizon problem, the flatness problem, the relics problem, in a completely different way. All of the resolution of these puzzles are based on properties of renormalization group flows. And that would have been another talk, which I don't have the time. What I focused today was a little bit in the discussion of the initial singularity, and we saw that this is related to the infrared finiteness of the quantum field theory. And we have seen that in a specific model, we can see that explicitly in the mechanism for the resolution. So what is the outlook? Okay, I guess a big question is whether there are any observable signatures of this singularity resolution. And this rests on the size of this term. First of all, I think there is an interesting connection with what Ed was discussing, because we also see that the singularity resolution would affect really the long wavelength modes. So it's really the same modes. And whether this is visible depends on the size of this term and its relation to how big it is relative to cosmic variance. So it could be that it turns out that it's too small to be seen because the small L region is also has a cosmic variance. So in a sense, I think this question will probably have the answer in the next couple of years. And now moving forward, I think it would also be interesting to understand to test these models also against galaxy clustering and other large-scale structure data, and more and more of this data are available today. Okay, thank you.
Yeah, thank you very much, Kostas, for this very nice talk. Let us first start with quick understanding questions. Joshua?
Yeah, thanks, Kostas. That was a wonderful talk. Also, I apologize to everybody for my April Fool's Day little Zoom background that I had on earlier. My apologies. My question is, what I didn't catch is whether the holographic cosmology explains the initial conditions problem, the question of the low entropy of the initial conditions. I wonder if you could just comment.
Yeah, I think it does explain it, because it just comes to the universality of infrared dynamics. So initial conditions in this case is what happens to the infrared of the quantum field theory. And this picture here, actually, I don't need to show it, but we know that infrared dynamics are universal. So the initial conditions, you don't have to fine tune it. It's completely natural.
Okay, but why do we start so close to the infrared, I guess, is the question then?
Well, I mean, this is, now you're asking, this is why the whole framework is correct. Okay, that I can only compare it with I can propose a framework and compare with observations. And the framework is that the time direction is inverse renormalization group flow. Okay. So that initial conditions, the earliest time is the deep infrared of the quantum field theory.
Okay, thanks.
If I go here, okay, this is initial, the further back you go, the earlier you are.
Mm-hmm. Okay, I see. Thank you.
Ding.
Hi. Question from a total outsider to holography. How do I understand why the IR singularity of the QFT is related to the space-time singularity in the bulk?
Yeah, that comes from, in a sense, the basic properties I described earlier. And so one of the main features of these gauge gravity dualities, which we have tested over the last 25, 30 years, is these three ones. And one of them is this UV-IR connection. So the UV of the one theory is the IR of the other one. So now what has been tested the most is from the site where the UV of the quantum field theory is the infrared of the quantum of gravity, and there's a whole formalism called holographic normalization that shows that precisely the infrared structure of the quantum of gravity is precisely that of the UV structure of quantum gravity. The quantum structure of local quantum field theory. Here we're using the same principle the other way around. So now the UV of the quantum gravity is the infrared of quantum field theory. So it's part of what holography is.
Is it an educated guess that from this principle that they're related, or do you have a derivation?
Yeah. So holography, and none of the holographic dualities have really been derived from first principles. So I would say they're more of a status of kind of a principle, and then you build on it.
So you assume that
this is part of the framework. It's like what I answered earlier in the previous question. It's part of the holographic framework. So you can see in all the models we have studied so far, there are a number of common features, and these are the common features. And then now you use this, and now you say this is the nature of quantum gravity. Ideally, you will want to prove it, but it's the same thing. In QCD we haven't proven confinement yet, but we believe it's true. We have, in a sense, checked the theory in the opposite regime, in the regime where it's asymptotically free. So similarly here, in this gauge gravity dualities, all of these features have been tested in one regime or another, but they haven't proven in complete generality. So here I have the model where now I'm going to compare it with data. So it's the data which is going to verify or falsify the model. And as you saw, the data are strong enough to falsify models. Like this mostly fermionic model is false, and all of these models could be very easily falsified. Like again, if you find where was my universal predictions, if you find that there is non-Gaussianity, which is local, or if you find equilateral where FNL is different than 5/36. I mean, this is so precise, just a pure number, 5/36. Suppose you found non-Gaussianity, which is equilateral and is equal to 2. This would falsify this model. So you get falsifiable models, which you can compare with data. And at the same time, there are lots of conceptual issues that you gain along the way.
Okay, I guess I have follow-up questions I can ask, but then maybe I should stop and let other people go. Thank you.
Yep.
Yeah, there are a few more questions. So let's just remember that we also want to bring Ed into the discussion again. But first, I give the next question to Rifat, and then we'll go through the questions that were put in the chat before.
Hi, I have a very naive question. So in one of your slides, you put the dual QFT to be in the reheating surface. And why did you make the choice and not put it into a future slice?
Because I do not know how to, this is something I have been working for a while now. So ideally, where is my diagram? Ideally, I would put it here. And ideally, I should be able to put it anywhere I want to. Just going to change the nature of quantum field theory. But currently, we do not know how to write down, let's say, the holographic dual of a radiation-dominated universe. I would love to know that. That's something I have been thinking about. But that's why I put it here, because here I know how to describe the theory that has for the very early universe. I do not have concrete models that could describe the universe here. I know how to describe, let's say, at the end of the time, if we have a cosmological constant and we get to the space-time, then again, you get into the region where you start to know how to quantitatively describe the universe, but not if you're somewhere over there.
And so let's say you put it in a future slice. So Are you saying that we can only know the past and not the future?
Yes, I think you can only know accurately, completely accurately the past, and only know the future in the neighborhood. The same way that we do it quantum field. If you do effective field theory, then you know the description up to the UV cutoff, the energies below that, and then you know, but you also know how to quantify what you don't know. I think it's similar in this case.
But in a future slice, let's say if I can measure everything, then ideally I would be able to say everything in the future, right?
No, that's not what this says. This says if you really measure everything, you know everything about the past.
So
and
there's
then
no
you have limited
predictability.
information about the future, because when I write the quantum field theory here, unless I give it completely non-perturbatively in a way that we don't know how to write currently.
This is only due to the bulk that
Okay.
in the past. Can I just ask? So in the normal like ADS CFT calculations, you do perturbative calculations in your ADS bulk, and then that's due to strongly coupled CFT on the boundary, right? So this is saying if you're going to take the same holographic principle, so like regardless of what your bulk spacetime is, then you're going to still be doing perturbative calculations, right? And saying that they're due to these boundary observables at the reheating surface, right? Correct?
Yeah, so if you want, and actually some of these computations have been done. So you can say, suppose you want to describe conversion and inflation, where polarity is perturbative. Yes. Then you can describe this with a strongly coupled quantum field theory. And actually you can do it quite generally. You can reproduce pretty much a general inflationary computation for the spectra and bispectra with general potential.
Yeah, like in the cosmological bootstrap, what we do is that the correlation functions the correlation functions are computed from a wave function of the universe that is assumed to be something that arises from a QFT and Kerr spacetime, right? That but that's not the same as this principle.
Yeah, we're not doing the QFT in Kerr spacetime. It's just quantum field theory in vanilla flat spacetime.
Yeah.
And that describes a curved bulk. But it would be the same as, let's say you start from n equals 4 million in flat space, and then the correlators describe an ADS cross a sphere space. And if the quantum field theory is close to be perturbative, then it would be in a higher spin phase of kind of a CLF type theory in the bulk. And if you start turning on quantum corrections, that would be the full string theory. So it is conceptually similar.
Thank you.
Okay, Deepankar, during the talk, you wrote a comment in the chat. Would you like to mention it now and have it discussed? Okay, it doesn't seem to be the case at the moment. So maybe I just go forward and ask Stefan, because he also wrote a question in the chat, whether you would like to ask it now. Oh, it seems
Okay,
Stefan
I see the question. Let me start from the last one, and then I'll read the previous one. So the question is, what choices do we have for the dual CFT? First of all, in most of this talk, I do not have a CFT. So this theory is not a CFT. Oops. And it's never a CFT because it has a dimensional parameter. So there's only a discrete number of choices. So it's really far fewer than conventional gravitational models, where in general you have freedom of the whole potential. So here the freedom is how many scalars you have and what are the coupling constants. So a discrete number of parameters. Now Now, if you want to describe models which are close to be inflationary, like what I was describing here, then you do have a CFT, and then again, you have a discrete number of choices, like here, say you'd perturb the theory by nearly marginal operator. So okay, how many of those operators you have, what are the CFT data for those, like the OP coefficients and so on. Has this answered the question?
Yeah, the person who asked the question has already left.
Okay.
Unfortunately. Maybe we go to one of the live questions again, and then maybe if there's time, you can respond to the other comment.
Sure.
Aaron, go ahead, please.
Yeah, I also have a specific question for Kostas, but maybe I can start with an overall question, because it seems to me like both LQC and this holographic picture, they are frameworks for general cosmological theories, right? I can write down different theories as the holographic dual, and I can add different meta theories to the LQC model. And my question is, like, this provides a lot of freedom in the choice of cosmological model, basically as much freedom as in GR. So can we really hope to distinguish sort of the frameworks, GR, LQC, and holography, if we have so much freedom in the choice of specific model? And this goes out to both of the speakers, so Ed and Kostas.
Well, I think at the end of the day, let me first give, and then maybe Ed can come in. I think at the end of the day, the models have to fit data first and foremost, whatever data we have. And then you can do model selection with the data, like what we did when we compare with lambda CDM versus holographic cosmology. And it could be that the data cannot decide. If the data cannot decide, then you can go and say, what are the theoretical advantages that one or the other approach gives you? What does it buy you? So I wouldn't say everything goes in these models, because they're not all quantum field theories or holographic. And then once you give the dual quantum field theory, that describes the entire universe. It's not a sector that I left out. So if I tell you that the full theory is given by this, this simple model, I haven't left matter system out. This is this is the full description. So if you want, let's say, to describe the standard model, okay, this means that I have to have a dual quantum field theory that has as a global symmetry as U3 cross U2 cross U1. And but then by the correlator, then I can work out the correlators of fields corresponding to the standard model, and then I can see whether I get correctly, let's say, the Higgs couplings. It is one of each of these Lagrangians is the entire universe. It's not part of the universe.
Okay, now I have many follow-up questions, but maybe we can get Ed to answer first.
Yes.
Yeah. So let me just answer your first question. I mean, you're absolutely right that in loop quantum cosmology, it really depends what you couple to it, right? So if you have an inflaton field, then you can pick a potential, and that could affect the predictions. I would say that, there's certainly no guarantee that you'll be able to distinguish between what's due to the choice of the matter field and what's due to quantum gravity. So there are no promises, but I think there is some hope still, because I know loop quantum cosmology best, so I'll speak about that specifically. But let's say we think that inflation is the correct early universe scenario, then the types of LQC effects that happen at large L seem to be quite independent to the potential that you pick. So you may choose the potential because you say, oh, I want a very flat potential, so I get a small transfer to scalar ratio, for example. So that's some observational input that's telling you about the potential. And then there may be some effects at small L in the CMB that then you could look at them and ask, okay, is this what you may expect from loop quantum gravity or quantum cosmology or not? So they certainly don't disentangle completely, but once you have an idea what you're dealing with on the matter side, then you can hope that you can look in more detail. But if you don't know, like, is it inflation, is it some alternative to inflation, then it's very hard to make general claims about what you could see.
Mm-hmm. Okay, but I think these sort of generic signatures of a whole class of specific models are what I was looking for. Thanks.
Yeah, if you're able to narrow it down and say, oh, we're looking at inflation with a flat potential, then the signatures are more robust.
All right, thanks.
Okay, Nyayesh, please go ahead.
Thank you. Thank you to both the speakers. So I had a few questions, but in the view of time, I'm just going to ask the most burning one. So there is a debate between, I guess, the LQC camp and Martin Bajewald, who used to be one of the, I guess, people who was on the same camp. So could you tell me what the debate is about and why he's wrong?
Okay, this is a big topic, but let me do my best. So I talked very briefly about the effective equations. Right, so if we have a homogeneous geometry and we look at sharply peaked states, then we have some effective equations that describe the dynamics of expectation values. And these are like almost classical equations, and they tell us how the expectation values evolve. Now, for the homogeneous background, this is well established. And it's hoped that maybe this can be used for perturbations as well. But this is less sure. Now, what Martin and some of his collaborators have done is that he's looked at that for perturbations. And so Martin and some collaborators and also other groups have looked at this. And in some cases, you have changes to the constraint algebra that show up. And these changes look like you're changing the signature of the space-time close to the bounce. And it's the interpretation of this which is at the root of the disagreements, I think. So I think one of the big questions is if you trust these results, then how should you interpret them, and how should you then impose initial conditions? Because of course, if you start having a Euclidean spacetime, then you may want to impose initial conditions in a different way. And part of the debate is whether these results are robust or not. So there are other people who have done some gauge fixing first and then looked at the perturbations in a different way, and they don't see this effect. So that's one point that has led people to argue, well, maybe this effect isn't real. And the other question is, even if it is real, then what do you do with it? Do you still want to impose your initial conditions in the middle of the bounce when it would perhaps be Euclidean and you may want to impose initial conditions in a different way? Or do you want to impose initial conditions before the bounce when it's still Lorentzian? And then if so, then how do you evolve through this Euclidean patch? So I think there are still some questions here as to whether this truly does happen. And if it does, how to handle it. So as I said very briefly in passing, all of the frameworks that we have are based on different types of approximations. And these results are based on using these effective equations, which we know work very well for the homogeneous background. And it's reasonable to hope that they may work well for perturbations, but it's really not guaranteed. So that's one thing that has to be understood a little bit better here. Does that help?
Thank you. Yes, it's very good. Thank you very much.
You're welcome.
So maybe, Joshua, if you're still around, you made a somewhat provocative statement. If you you want to pose it to our two speakers?
Sure, yeah. It seems that a lesson from both of your talks might be that it's not so difficult to get a nearly scale invariant spectrum of initial density perturbations without inflation. So I just wonder, is that an accurate characterization of the situation? Is this reason not to necessarily hope for inflation?
Well, maybe let me go first. Kostas may have a slightly different take on this. My point of view is that inflation works very well at giving you scale invariance. It's not the only way, so there are other ways to do it. But I would say that the other ways are relatively few. So I can think of a handful of ways that will give you scale invariance. So certainly not only inflation, but there aren't, it's not that you can do anything and you'll get scale invariance. That's certainly not true. But there are, a handful of other ways that you can get something which will be scale invariant or nearly scale invariant. That said, inflation does seem to be one of the easiest ways to generate it. So that's why there's a lot of interest for that.
Okay, so maybe if I go now, I think from my perspective, this mechanism I described is more general and requires, in a sense, less than in inflation. So in inflation, you essentially use at late times where the space-time becomes de Sitter, you have the de Sitter symmetry is the same as conformal symmetries, and this gives a scaling that this gives this factor of q cubed here, which is, and then if you have a CFT, this f is a constant that gives you the scale invariant spectrum. So you use the symmetry that you have this scaling symmetry at late times. So this new mechanism in this non-perturbative theories, you use something which is a little bit less, you use less of a structure. You use the fact that if you have an energy momentum tensor in your theory, its dimension is going to be the same as the space-time dimension. That produces the same factor q cubed without having the scaling symmetry. And then the violation of a scaling symmetry comes from the fact that the theory is perturbative. So if I look at this f, so to leading order, this is a constant because this is an one loop computation, and then you have small correction because these are perturbative. So indeed, this is a more general mechanism. It does incorporate inflation as well. If you add more symmetries, then you get the inflationary mechanism. But it is more general because you don't need the scaling symmetry. And in these models, this non-geometric models, you really do not need this exponential expansion of space-time. So it does. One can call them also as alternatives to inflation because it does the same thing without using the exponential expansion.
Great, thanks.
Okay, I don't see any questions at the moment, so maybe I might pose a question towards both speakers. So you presented, both of you, your favorite theories that you're working on where you see a singularity resolution of the Big Bang singularity. And Kostas, if I understood you correctly, because we're basically looking at this at the on the QFT side, you basically have no understanding what the quantum space-time would be, or what what.
Yeah, it's non-geometric. So it's non-geometric. Mm-hmm. So from our perspective, in a sense, we don't have a language to describe it beyond the holographic dual. So so it could be that this could be described in some string theory model at where the sigma model is strongly interacting, but no one can solve those. So this is, in a sense, the only way to do the computation. But then you have a way to start from the resolution and transfer this into observable quantities, and then ask whether this agrees or not with what we see.
Mm-hmm. And Ed, from your perspective, from LQC, would you say that I mean, the expectation would be that classical space-time breaks down, but it looks rather well behaved if you look, for example, at the effective dynamics. So is that just, you know, a certain effect if you are highly peaked on semi-classical states and you trace the evolution back, or what is your?
Well, it also has to do with the degrees of freedom that you're looking at. Okay, so here you're really looking at the degrees of freedom corresponding to the scale factor. So these are very large scale degrees of freedom. And it's those degrees of freedom that are heavy in the sense that quantum fluctuations, you know, if you choose a state where these quantum fluctuations are initially small, they'll tend to stay small. But if you're looking at our universe, you know, at the bounds and quantum gravity effects are important. And instead of just looking at these, you know, large scale degrees of freedom, like the scale factor, you're interested in local quantities, then your quantum fluctuations could be more important. And indeed, like if it, essentially the smaller the region of space that you're looking at, the larger quantum fluctuations will become important.
Mm-hmm. And would you say that, do you expect, you know, for example, the bounds also to be robust in, if you would use a full theory of quantum gravity, like if you had full LQG available, or you would do spin foams or GFTs? I mean, for GFTs, there have been a few examples where you also obtained the bounds.
That's right. So I think there's still more work to be done there to really make the connection as clear and precise as possible. But all of the early indications show that the bounce is still there. And so that appears to be very robust.
Okay, then maybe last quick question. What do you precisely mean by heavy? That the degrees of freedom like are heavy?
So just for example, if you're looking at a hydrogen atom, right, it's reasonable to say that the proton is at the origin, and then we treat the electron in a quantum way. And the reason why we can do that and not the inverse is because the electron is light and the proton is heavy. So it's just taking this language from quantum mechanics and using this other context. In other words, so we know that the uncertainty relation between x and p is bounded by h bar over 2. But typically in a lab, we'll really be measuring x and x dot. Right, so we have a particle, we know its mass. So we're really measuring x and x dot, and the uncertainty between x and x dot is h bar divided by m. So if m is large, then we can know its position and its speed quite accurately. So that's what I mean here. It's just an analogy with that.
Okay, yeah, thank you. And I do not see any further questions at the moment.
Can I ask one quick question for Kostas? So I was curious about this dual picture between the renormalization group and evolution. And so as you explained, that means that evolution forward in time isn't entirely predictive. So I was wondering if there would be any consequences we could look for based on that.
That's a very good question. Yeah, I don't know. The quick answer is I don't know. But I mean, it is interesting to think because it's really conceptually different.
Yeah, very much
and
so.
One could try to think, you know, can you actually come up with something that it would be observable? Yes, yeah.
Yeah. All right, thank you.
So can you say something about choosing the system so that entropy of the universe from the Big Bang decreases? Let's say if we choose a system pre-Big Bang, then after Big Bang, the entropy may decrease and the entropy of the environment may increase.
I think from a perspective of the dual quantum field theory, you don't have this. You don't have different subsystems. The whole it's one system. So as you go to the UV, you have more degrees of freedom. It's like, you know, you're looking at the quantum field theory. It's the normalization group flow gives you a cross graining of the system from the UV to the IR, and you start from in the very deep IR, the fewest degrees of freedom, and then in the deep UV are the most degrees of freedom. So you do not separate between the system and the environment. This describes the entire the entire universe.
Okay, thanks.
Yeah, and for my my side, I would say the same thing is true in loop quantum cosmology. We haven't separated this into a system and an environment or anything like this. We have the whole universe, and that's everything. That doesn't mean that you couldn't then introduce some sort of separation, but that's not something that we've done. So I don't have like a strong answer I can give to that possibility, because then you'd really have to say, oh, this is some subsystem we're looking at, and somehow I do some work on this subsystem which decreases the entropy there. But yeah, I mean, it's an interesting question, but I don't have a strong answer at this point.
Okay.
Okay, so it seems that there are no questions at this moment. So I would like to very much thank Edward and Kostas again for their great talks, and all of you for sticking around for so long and having such an engaging and very interesting discussion. If you want to continue discussing, the Slack channel is available. If you have additional questions or follow-ups to Kostas and Ed, we will relate those. And our next talk, we will announce the date for that in May, hopefully soon, will be with Steve Giddings and Hal Haggard on black holes. So stay tuned. Thanks everyone for joining today, and thanks again to Ed and Kostas for their great talks, and see you next time.